Hello and welcome to another episode of Paper Talk. Today we have with us Miss Shalini Kumari, who completed her MSc from Banaras Hindu University and currently she is pursuing her PhD in the Department of Inorganic and Physical Chemistry at the Indian Institute of Science, Bangalore. Today she will present her talk on the art of molecular surgery from traditional synthesis to skeletal editing. So Shalini, welcome to the talk and the screen is yours.
Thank you for giving me this opportunity. So in this talk, I will talk about transformation from traditional synthesis to skeletal editing. So first we will start from our traditional synthesis. So in our old way, we are making any complex molecule from scratches by making every bond step by step, just like an architect. How architect is building any home? Architect is building any home by making every wall step by step. So in our old way, we chemists are also making any complex molecule by step, forming every bond. But this method has so many limitations. Like this one is laborious, time consuming, and often wasteful. Now imagine we have synthesized any complex molecule, and for some reason we just want to change any functional group or any small atom. But even for this small change, in this method we have to take entirely new synthetic route by making this complex from scratches again, which is making this method limited for late stage modification and also inefficient for exploring new chemical species. So then we chemists realize then we need renovation, not reconstruction. So to overcome these challenges, we took inspiration from a term called genome editing. So basically what is genome editing? Genome editing is discovered by biologists to edit any organism DNA without affecting the other part. So after discovery of this, we chemists also began dreaming, like can we also edit our molecule in the same way how biologist is editing gene? Can we also edit the same way? So this dream gave birth to a new era which is known as our molecular editing era. Now, basically, what is this molecular editing era? So, in this molecular editing era, we start modifying our directly existing molecule instead of synthesizing every time from the scratches to alter their function, properties, or activity. Now, let's suppose this one is any complex molecule and this green ball is any functional group and we want to change this functional group only. We don't want to affect the other portion of this molecule. Or let's suppose instead of this 5 membering, we want 6 membering, or we want to change the position of this functional group, this green ball, instead of this carbon to this carbon. Or let's suppose we just want to change only one atom, like the atom which present here, we just want to change this atom. So this all type of editing is comes under the molecular editing. So in this era we start modifying our existing molecule like this. So this molecular editing has two parts of editing. First one is peripheral editing, which is well established, and second one is skeletal editing, which is still underdeveloped. Now we will start from our first generation of editing, which is known as the peripheral editing. So Professor Sarpong revolutionized this editing era. So he is known as the pioneer of this peripheral editing era. As the name itself suggests, in peripheral editing era, we start modifying at the outer parts of the molecule. If we will see this example, so in this example, all the modification which has been done in this molecule is only at the outer part of the molecule. The inner part, like the skeleton of the molecule, which is inside this circle, is still intact. Or in real life example, we can say that it is just like a cosmetic touch-up. Like we are putting makeup on a molecule to look stylish, but underneath both the molecule have same skeleton. So this editing is changing appearance, not the identity of the molecule. So this editing includes CH activation, atom functional group exchange, stereochemical editing, functional group transposition. This all type of editing is known as peripheral editing. It leads to the change in molecular behavior like solubility, reactivity, or biological activity. So from this editing, we chemists realize that this method is fast, easy, but limited. Then we move towards our second generation of editing, which is known as the skeletal editing. So Professor Mark Levin is the pioneer of this skeletal editing era. He is known because he revolutionized this skeletal editing concept. During his graduation time, one thought came into his mind like, can we transform this benzene to pyridine or pyridine to benzene or simply like pyrrole to furan, furan to thiophene? Can we do this type of transformation? This chemistry is not a new chemistry, it is century old chemistry. But before him, no one able to do this type of transformation in one pot. So his curiosity leads to a new era which is now known as the skeletal editing era. So skeletal editing is basically a atomic level surgery where we are performing surgery on a molecule by removing one fragment and we are skillfully attaching the another fragment. So now what is this skeletal editing? So in our second generation of editing, that is skeletal editing, we start modifying the molecular's code framework and like skeleton of the molecule. Let's suppose this one is any 5-member ring which is present in our complex molecule, but we want to modify this ring. Instead of 5-member, we want to modify it to 4-member, or we want to modify it to 6-member, or let's suppose we just want to change only this atom. That this blue atom we just want to replace with this purple atom. So this all type of editing is known as the skeletal editing. So this skeletal editing leads to change in the fundamental identity of the molecule. Like let's suppose we are transforming benzene to pyridine or pyridine to benzene. Here in this transformation, if you will see carefully, there is only one atom replacement like carbon to nitrogen or nitrogen to carbon. But still this editing is changing the identity of the molecule. Both benzene and pyridine, both is having different identity. Both are not same. Or in real life example, we can say it is just like a gender affirming surgery which leads to the change in identity of the person. So in this editing, there are three strategies involved. First one is atom deletion, second one is atom insertion, and third one is atom swapping. Now let's start our first operation, which is atom deletion. So atom deletion is just like removing a damaged bond and again rejoining it to recorrect the shape of our skeleton. So it can be any atom deletion, it can be nitrogen deletion, carbon deletion. So in both the example, we can see that when we are deleting this nitrogen atom, then it is giving the CC couple product, and when we are deleting this carbon atom, then it is giving the ring contracted product. So to explain this one, I I am presenting the first paper which is showing the skeletal editing through direct nitrogen deletion of secondary amine. So in this paper, what they did, this paper is published by Labin Group in 2021. So in this paper, what they did, they transformed secondary amine into CC couple product by developing a reagent which is known as the anomeric amide reagent. Why it is called anomeric amide? Because if we can see, then here this nitrogen is substituted with two heteroatom, which is an oxygen atom, and it is similar, it is analogous to the anomeric carbon which is present in the sugar atom, and that anomeric carbon is also substituted with two heteroatom in our sugar. So and that's why it is known as the anomeric amide. Since in this case this nitrogen is attached with two heteroatom, so due to which it becomes electrophilic in nature. So for this transformation, author has proposed some mechanistic hypothesis. So in this mechanistic hypothesis, what they propose that the first step is the nucleophilic substitution, where this NH of the secondary amine is acting as a nucleophile and this nitrogen of this anomeric amide is acting as an electrophile. So first step is the attack of this nucleophile to the electrophile, and which leads to the formation of this nitrogen-nitrogen bond. Now, since this intermediate is not stable because here it is forming nitrogen-nitrogen single bond, so it is immediately going into reductive elimination and giving this isodiazine type of intermediate, which is still unstable. So that's why after releasing this N2 group, it is forming a diradical species. And both the diradical is in close proximity. So that's why it is going into the in-cage radical coupling and giving this CC couple product. What do I mean by in case? In cage means that both the diradical enclose in the solvent cage. Here solvent is acting as a cage. That's why it is forming in case diradical coupling CC couple product. So after developing this reagent, they start optimizing this reagent. So in the first case, when they took the simple 1A anomeric amide, in this case they got only 35% of their desired product, and major product is this one side product. Because in this case we can see that there is a possibility of attack of nucleophile at both the center, either at this carbonyl center or at this nitrogen center. So to prevent this nucleophilic attack at this position, they substituted this methyl group with bulky tertiary butyl group. And in this case, we can see that the yield is increased up to 57%. Now, in another case, what they did, they substituted this phenyl ring with electron withdrawing group to make this nitrogen much more electrophilic. Then they got a surprisingly result that in this case yield is increased up to 74%, and it gives 100% conversion only in 5 hours instead of 18 hours. For that they did some Hammett study. So in this Hammett plot, the plot is against the rate on the y-axis and this electrophilic substitution constant on the x-axis. So in this case, they got positive slope, which is indicating that rate of reaction is increasing with electron withdrawing property of this X group. But since they are not able to make the more electron withdrawing group containing anomeric amide, both the electron withdrawing power of this X is more than CF3, so they didn't able to make this anomeric amide. So they only give the example of this CF3 substituted anomeric amide. But here this result is indicating that the electrophilic center is involved in their RDS step. So after reagent development, they did some control experiment to study the mechanism, like in the proposed mechanism is matching or not. So first step, what they proposed, that nucleophilic substitution. So to prove this step, what they did, they studied this reaction with different polar solvent. They change the polarity of solvent. In that case, what they observe, that there is a minimal effect of solvent polarity in that case. So from here, what they concluded, that there is a less charge separation in their transition state. So maybe it is going through nucleophilic substitution pathway. Then another step, what they proposed, that formation of isodiazine intermediate. To prove that one, what they did, they took this allyl secondary amine, and when they treated this one with this anomeric amide, then it is giving like it is rearranging through this 2 3 sigma tropic rearrangement, and it is giving this isodiazine type of intermediate. Then to prove next step, that after N2 gas releasing, it is forming this diradical coupling, they took this unsymmetrical secondary amine. So in this case, we can see that when there is a no tempo, then it is giving the 93% of this intramolecular product, and another 7% is this intramolecular product. But when they added the tempo, then it is only giving the 100% of intramolecular product, because this intramolecular product, which is forming out of cage, is scavenged by this tempo radical scavenger. So from here they confirm that it is going through this in case radical coupling. And to prove the last step, that is it is really going through radical intermediate, they did this radical clock experiment. So for that what they did, they took this cyclic propylamine. So in one case there is no substitution, and in another case there is substitution with pH group. So from here we can see that when there is a substitution, then rate of ring opening is fast in case of pH substitution, and it is going into the rearrangement. So when there is a pH substitution, then they got rearranged product also, but when there is a no substitution, then they didn't absorb any rearranged product. And also rate of ring opening is slow, when because here we can see that rate in case of pH 10 to the power 11, and rate in when there is a no pH, then here it is the rate is only 10 to the power 8 per second. So from this experiment what they have concluded that it is really going through the radical intermediate. After mechanistic investigation, they have shown a lot of substrate scope, in which case first they have shown the functional group compatibility. So in this here we can see that their method is applicable to a variety of functional group like phosphate functional group, amide protected functional group, free OH, and nitrogen containing heterocycle. In all the cases their method is compatible. After that they have shown the skeletal diversity, which is the main highlighting feature of their method. If we will take in a cyclic amine and if we will apply their standard condition, then it will give this ring contracted product, which is the example of skeletal remodeling. After substrate scope, they have shown some application, because the main motive of our skeletal editing is that the method should be applicable for the late stage editing of our drug or complex molecule. So for that they have shown some application. In the paper they have shown 4 or 5, but here I am showing only 2. So first application what they have shown the application of this chemotherapeutic agent synthesis, which is used in the treatment of lung cancer. And another application they have shown is the synthesis of bioactive compound. In this case we can if we will see carefully, then it contains 2 NH, but their method is selectively deleting this NH or it is not affecting the other part or this NH. So they have shown the example of chemoselectivity also. So in this paper we have seen they developed a practical nitrogen deletion reagent. They have shown high functional group tolerance. They enables ring contraction and skeletal remodeling. It is valuable for late stage modification, and also their method develops a new paradigm in synthesis. Now let's come towards our second operation, which is an atom insertion. So it is like placing a small metal mesh tube into our blocked or narrow artery to improve their function. So this both example is the atom insertion. First one is the carbon atom insertion and second one is the nitrogen atom insertion. In both case we can see that the atom insertion is giving the ring expanded product. 5-member ring has been expanded to 6-member ring in both the gases. So there are some examples in our traditional chemistry of atom insertion also. First example is Baeyer-Villiger oxidation. So what is Baeyer-Villiger oxidation? So in Baeyer-Villiger oxidation, if we will take a normal ketone, so in the presence of per acid, it will give this ester, which is nothing but the oxygen atom inserted product. Second, if you will take a cyclic ketone, then it will give this cyclic ester, which is a lactone. And this both is the example of oxygen atom inserted product. But it has limitation because it can only insert atom next to a carbonyl functional group. Then another example is siamicin denstate rearrangement, in which case it is in situ generating this dichlorocarbene intermediate, which is after inserting into this pi bond giving this carbon atom inserted product. But it also has limitation because it can damage peripheral functional group. So to overcome this type of challenges, we developed some method for atom insertion through our skeletal editing method. So for that I am presenting the second paper, which is published by Lu group in 2025. So in this case they have shown the example of nitrogen atom insertion in pyrrolidine rings. So why they choose the nitrogen atom only? Because N-heterocycle are common in more than 80% of modern drugs. This is the US FDA approved data. So in this data we can see that 82% of modern drug contain N-heterocycles, and in this 82%, most common is six membering N-heterocycle, after that 5-member, and then fused ring. So from here we can say that in this nitrogen atom is serving as a critical element for tuning molecular recognition and physiochemical profile. Survey, what they found, all the example what is given is showing the nitrogen atom insertion in aromatic system, which is a pi activated system. But they're not able to find an example of nitrogen atom insertion in saturated heterocycle because it is very challenging. So after taking motivation from this, they developed a reaction methodology. For in this case, they developed a reaction. So for that they took this commercially available DPPH reagent, which is ortho diphenyl phosphenyl hydroxyl amine. And by using this reagent, they able to insert this nitrogen atom into this pyrrolidine, which is a saturated and heterocycle molecule, and they synthesize this tetrahydropyridazine molecule. This molecule has a very unique feature because it is having carbon-nitrogen double bond, which is very reactive in nature, and it also contains NH, which is a nucleophilic in nature. So if we will reduce it, then it will give this fully saturated piperidazine molecule. And if we will oxidize it, then it will give this pyridazine, which is an aromatic compound. And both the moiety is very valuable in our drug chemistry. So after developing the method, they start optimizing their condition. So in condition first, we can see that when there is a no deviation from their standard condition, then in that case they got 68% yield. And when they change the base KOH, which is a stronger base, instead of K2CO3, then their yield has been decreased. So from here, what they have concluded that maybe their method is dependent on the strength of base. And in another condition, also when there is a no deviation, then they got highest yield, which is a 50%. And when they apply cross condition in both the cases, then it is not giving a good yield. So from this optimization, what they have concluded that maybe their method is substrate specific. Like for proline derivative, condition 2 is effective, and for another condition 1 is effective. After optimizing, they did some control experiment. For that, first they did the isotopic labeling experiment, because in the product is having two nitrogen atom. So to check this nitrogen atom is inserting on which side, either this carbon nitrogen double bond or carbon nitrogen single bond, they did this experiment, and in this analysis what they found that it is this this nitrogen atom is inserting into this carbon nitrogen double bond side. There is no product observed, like this insertion of this nitrogen atom into this carbon nitrogen single bond. After this they perform another control experiment, because what the mechanism they were thinking in that there is a possibility of formation of this diazotine intermediate. So for that they individually synthesized this intermediate and they applied their standard condition. So in this case there is no nitrogen inserted product formation was there. After this, they proposed a mechanism. So in the mechanism, the first step is the formation of isodiazine intermediate. Like if we will take this pyrrolidine molecule and if we will treat with DPPH, then since they are taking two equivalent of DPPH, so it is giving the two successive addition of this NH2 and it will form this triazonium intermediate. And after releasing of this NH4 plus group, it will immediately forms this isodiazine intermediate. Then another step what they propose is the transformation of this isodiazine intermediate. So after formation of this isodiazine intermediate, there are two possibilities. First possibility is through 1 to sigma migration, it can form this diazine intermediate, or through 1,3 hydrogen shift it can form this 1,3 dipolar intermediate. So if it will go through this path 1, so in this case diazine intermediate have 2 nitrogen which is equivalent in nature. So if after this when it will go to the 1,3 hydrogen shift, then there is a possibility of both type of product formation. But from the isotopic labeling experiment we have seen that there is no product formation like B dash in their analysis. So this path has been ruled out from their isotopic labeling experiment. Then another possible pathway is formation of 1,3 dipolar intermediate through this 1,3 hydrogen shift. Then it still has 3 route. So in the first route what they propose that after that it can go to the 1,2 sigma migration, it can form the product like B dash, but it is contradictory to their isotopic labeling experiment, so this path has also been ruled out. Then another possibility is it can cyclize to form this diazurin intermediate. But in their control experiment, they have shown that when they applied their condition in diazurin intermediate, then no nitrogen atom inserted product has been observed. So this path has also been ruled out. Then an only possible pathway is that first it will go to the ring opening and will form this hydrogen aldehyde type of species, and then or hydrogen oxonium ion type of species, then it will immediately cyclize to give this nitrogen atom inserted product. Then they have explored some variety of substrate, in which case in the paper they have shown a variety of substrate like alpha substituted, beta substituted, then asterically hindered substrate, proline derivatives containing substrate, and after the monocyclic they have shown some polycyclic ring containing substrate like fused ring, spiro ring, bridge architecture. In all the cases their method has been widely applicable. So after reaction scope they have shown some application for late stage editing of drugs and complex molecule. For that first they have shown the example of this pyrrolidine containing drug, which is a celtodextrin and which is a allosteric modulator of dopamine receptor. In this case when they applied their standard condition, then they able to get this nitrogen atom inserted product. And another example what they have shown this tetrahydroisoquinoline scaffold containing this natural product. In this case also their method is applicable and they got this nitrogen atom inserted product. Then after that, to explore more, they synthesize some hybrid molecule which contain both natural product and drug molecule. So in both the cases, we can see that their method is applicable with a moderate yield. After that, in this substrate, from the substrate scope, what they realize that their method is mainly applicable for this nitrogen atom unsubstituted product when there is no substitution at this nitrogen center. But in most of the bioactive molecule, this nitrogen atom is substituted. So to overcome these challenges, they modify their method. For that, they have shown the another two example. So first example what they have shown the nitrogen atom insertion of meticllinide. It is an anti-diabetic drug. So if we will take this one as substrate and if we will treat it with this S3-benzyl dihydrofuran 2,5-dienone, then it will give this meticllinide product. But in this case, what they did, first they applied their standard condition and they got their nitrogen atom inserted product. Since their nitrogen atom inserted product, they still have this NH which is nucleophilic in nature. So after that they substituted this NH with side group and they got this nitrogen atom inserted like isomer type of thing of meticllinide product. And another example what they have shown that nitrogen atom migration of glyclazide, which is also an type 2 diabetic drug. So for the synthesis of this glyclazide, this upper method is already known. So in this method, they modify this one. First, they apply their standard condition. Then they treat this one with paratolvin sulfonyl isocyanate and they got this nitrogen atom substituted product. And when they reduced this one with any presence of any reducing agent, then it is giving this in this 3D product, which is the nitrogen atom migrated isomer of this glycylazide. So in this case, they have shown the example of scaffold hopping. So in this paper, we have seen that they enable scaffold hopping without de novo synthesis. They they expanded structural diversity. They developed first general method for nitrogen atom insertion in saturated heterocycle, and also they opened pathway to new nitrogen-rich pharmacophores. Now comes towards our last operation, which is which is a atom swapping. So in this case, here we can see that first example is the carbon to nitrogen atom swapping, and another example is oxygen to nitrogen atom swapping, which is an example of furan to pyrrole transformation. So it is just like like organ transplant. We can say that we are replacing our damaged organ to another to another like some kind of heart transplant. We can say we are replacing our damaged heart to new heart to improve to improve our function. So to explain this one, I am presenting the last paper, which is the example of carbon to nitrogen atom swap, where they have shown the synthesis of benzimidazole from indole's molecule. So why they choose the synthesis of this benzimidazole? Since from the last slide, previous slide, we have seen that N-heterocycle are very common, and in N-heterocycle, this indole molecule is very common in drug molecule. But some is indole has some limitation because in indole this 5-member ring is electron rich in nature, due to which it is having a metabolic hotspot at C2 and C3 position, which is giving some toxic uh, profile. So to overcome this type of limitation, if we will substitute this one carbon with this nitrogen, then this ring will become electron deficient, and it also will remove one metabolic hotspot center. So if we replace this one carbon with nitrogen, then it will improve metabolic stability and potency. What do I mean by metabolic stability? Like if we are taking any drug molecule, then the enzyme which is present in liver try to destroy that drug molecule, and this enzyme mostly attack at the electron rich center, or the center which is prone to oxidation. This type of center they attack very fast. But if we will replace this carbon with one nitrogen, then this ring will become electron deficient, and also it will remove one metabolic hotspot, so they will resist this one, and their half life will increase, due to which it will improve their metabolic stability. And since by replacing this nitrogen, it is creating one more binding site, which is like increasing the drug target interaction, it is making better, due to which this drug become more potent, like even a small amount of drug is very effective. So that's why they want to synthesize this benzimidazole. So for this synthesis, they did some literature survey for the carbon to nitrogen atom swapped product. So they did this type. They found these 3 methods in their survey, but in all the method, what they found that substrate pre-activation are required. So from here they got a motivation to develop such kind of method, in which case we can directly convert an alkyl indoles to benzimidazole without any pre-functionalization. So for that, to develop this strategy, they start using the intent property of indole. Like indole is very prone to oxidation. So in this strategy, what they thought, they will use the first step as the oxidative cleavage through Wittkopf oxidation, which will lead to the formation of this Wittkopf type of intermediate, dicarbonyl type of intermediate, which will then go to the oxidative amidation, followed by Hofmann type rearrangement. Then in the last, it will cyclize to give benzimidazole type of product. So for this transformation, they developed a method using simple commercially available reagent without any pre-installed functional group. For that, they choose this reagent, which is a PIDA and ammonium carbamate. So why they choose this one? So they know that this after oxidation of this indole, it will give this dicarbonyl type of product, which is a Wittkopf intermediate. Then they start thinking all the possible rearrangement from this type of intermediate. For that, they took different type of electrophilic nitrogen donor containing reagent. So in this case, when they use this hypervalent iodine containing reagent PID and ammonium carbamate, then they got at least 15% yield. That's why they choose this reagent. So after that, they start optimizing their reaction condition. In this case, what they found, when they used excess amount of ammonium carbamate and PIDA, then they got 100% conversion, but still they got only 42% of their desired product, other is the side product. But when they further increase the amount, then it is giving more amount of side product. After optimization, they start performing some control experiment to prove their mechanism. So first they perform this control experiment. So for that, first they took this 5-methoxy indole and 5-methoxy indole. So in this case, when they applied their standard condition, then they got dinitrile product, which is a possible when there is over oxidation in Wittkopf oxidation. So from here, what they concluded that maybe it is going through the Wittkopf oxidation. To confirm that, they directly took this Wittkopf intermediate and they applied their standard condition, and they got this nitrogen atom swapped product in like similar amount. And after that, what they think, since they are using emanating source like ammonium carbamate, so and they are also using this oxidizing agent like PID is a oxidizing agent also. So we have aldehyde also or amines also. In the presence of oxidizing agent, it can form this amide bond through the oxidative amidation. So for that, they directly took this intermediate and they apply their condition. So in this case also, they got this nitrogen atom swapped product with similar yield. So from here, what they concluded that it is going through the oxidative cleavage of indole, and from here, there is a possibility that it is going into the Hoffman type of rearrangement, and after that, after cyclization, it is giving this and like carbon to nitrogen atom swapped product. So after performing this control experiment, they move towards explore some different type of substrate. So in this case, they have shown a lot of examples. So first, they have shown the example of alkyl group substituted this indole ring, then another nitrogen atom containing heterocycle. Then they have shown a variety of functional group tolerance. In this case, we can see that they have shown a lot of functional group like benzyl protected, free OH containing, free acid containing, all type of functional group has been well tolerated in their reaction condition. So in this indole, the C4 and C7 center is very reactive, but still they got this swapped product when there is a substitution at this position. After reaction scope, they have shown some application to late stage editing of drug-like molecules also. So their method have shown a variety of functional group tolerance, and it is widely applicable. So in this method, we have seen that they developed a one-step carbon to nitrogen atom swap using PID and ammonium carbamate. This reaction is proceeding by oxidative cleavage, amidation, and rearrangement followed by cyclization. They have shown broad substrate and functional group scope, and they demonstrated practical relevance through late-stage editing of drug-like molecules. And it is having a significant advancement in molecular editing chemistry. So up to this, we have seen that in our old era, we were like an architect. After that, the another era, which is the molecular editing era, came, in which we chemists became designer and we start directly modifying our existing molecule. Then now the era, which is a skeletal editing era, came, where we chemists became a surgeon. So in this era, we have seen the example of first one is the transformation of secondary amine to CC coupled product through nitrogen deletion. Then another example we have seen that in nitrogen atom insertion in saturated heterocycle. And in the last, we have seen the example of atom swapping, where we have seen the synthesis of benzometazole from indole ring. Thank you.
Nice presentation, Shalini. If you enjoyed this session, don't forget to like, share and subscribe. We'll meet you in the next episode, next session. Thanks for watching.